Okay, well, if not, then I thought we'd go over the worksheet together. So there's a worksheet I posted on my website, and then also on B courses. It just kind of goes over some diagonalizability questions. So why don't we start with that? So we're given a linear transformation from R2 to R2. And it's defined by what it does to two vectors, E1 and E2. So T of E1 is 2, -2. And T of E2 is -1, 3. Okay, and our goal is to diagonalize T. So we should figure out what that means to diagonalize a linear transformation as opposed to a matrix. And then we should try to see what that really means. So why don't we first start by writing T as a matrix. Writing T as a matrix. So how do we do that? So we've done this before. Right, so our matrix, since T is going from R2 to R2, our matrix should be 2 by 2. And the first column should be T of our first basis vector, and our second one should be T of our second basis vector. Right, and so we're going to put those in directly. We don't need to worry about other bases. We're just giving you the standard basis for now. Yeah, okay. Maybe if you want to convince yourselves, you can check that T of E1 indeed equals A times 1, 0, for example. Okay, so now we want to find eigenvalues and eigenvectors of A. Eigenvalues of A. Okay, so there's a multiple choice here. If we want to look for eigenvalues of A, which one of these is true? So we want the matrix A minus lambda I to be invertible. We want it to not be invertible. We want the matrix A to be invertible, or we want the matrix A to not be invertible. Okay, so maybe everyone think about it for about 5 seconds or so. Try to convince yourself.
Can you repeat the question?
Oh yeah, the question is printed on the worksheet. So if we want to find eigenvalues of A, what matrix do we want to test whether it's invertible or not? So there's 4 options. We want to know whether A minus lambda I is invertible, A minus lambda I is not invertible, A is invertible, and A is not invertible. Right, and so we just want to know which one is the correct one we want to look for. Right, and so we want A minus lambda I not to be invertible. Right, because if A minus lambda I is not invertible, then that means there's some vector in its null space, and that's the eigenvector. Right? So we're looking for scalars lambda such that A minus lambda I is not invertible, which is equivalently, what does it mean for a matrix to not be invertible? So there's again, 4 options. A matrix B is invertible if, and then you have some options here. So this is just kind of a review matrix. This is a review of previous weeks. Matrix B is invertible. Well, I'll just skip to the answer on here. Equivalently, we want to find, we want to test whether its determinant is 0 or not. So if it's not invertible, we want the determinant of A minus lambda I equal to 0. Okay, and so we call this the characteristic polynomial of A. So this is maybe we went over this last discussion as well, but it's still more review. So we want to find the characteristic polynomial of A, and we want to see what values of lambda give us 0. Okay, so we do that. Okay, so I'm going to clear. I'll save this. I'll clear this. Okay, so we look at the determinant of A minus lambda I. I already erased A, but I'll write it again. So the A was 2 minus 2, negative 1, and 3. Subtract lambda times the identity. All right, and so we just solve for this. Lambda squared minus 5 lambda. I think we actually did this exact one last week, maybe not. Okay, so we find that the eigenvalues of A are 4 and 1. So there's 2 eigenvalues because our characteristic polynomial is lambda minus 4, lambda minus 1, and 4 and 1 are the values that make this 0. All right, so in fact, we learned a little theory last week in lecture that we can actually tell immediately whether this is diagonalizable or not. So I'll put this in blue. So this actually implies A is diagonalizable. And why does it imply that? Well, it implies that because there's this theorem that says if you have a matrix, an n by n matrix, and you have n distinct eigenvalues, then you're diagonalizable. And so that's what we have here, because A is 2 by 2 and has 2 distinct eigenvalues. So it's automatically diagonalizable. But let's just diagonalize it anyways. If we didn't know that, let's see if we can figure out how to diagonalize it. So if we didn't know that, then our third step would be, let's find eigenvectors. Okay, so to find eigenvectors, we do it separately for each eigenvalue again. Lambda's 4, and lambda's 1. And we solve for x in the equation A minus 4i. So A minus 4x is minus 2 minus, or A minus 4i. We plug in 4 for lambda up here. And we find that x is in the span of a single vector, which is 1, negative 2. To keep consistent with the worksheet, I'll do negative 1, 2. All right, and the same thing over here. And we find that x is in the span of 1, 1. All right, so we found our eigenvalues and eigenvectors. So our eigenvalues are lambda is 1 and lambda is 4. And our eigenspaces for each eigenvalue, here we go. And this is the eigenspace for lambda equals 1. This is the eigenspace, oops. the eigenspace for lambda is 4. All right, and so now that we find the eigenvectors, we now can conclude that A is diagonalizable. Right, so how do we conclude that? Let's see. Feel free to stop me with any questions, by the way. So we conclude that A is diagonalizable because the eigenvectors, because there is a basis of R2 consisting of eigenvectors of A. This is what it means to be diagonalizable, right? That there's a basis that consists only of eigenvectors of A. And so in fact, we can write A as PDP inverse. So A is, I'll write that again, 2, -2, -1, 3. And let's write this as some matrix P times some matrix D times P inverse. All right. And so we can just do this like we've done before. So D, we want to be diagonal. So that means zeros on the off diagonals. And then the diagonal entries are going to be our eigenvalues. So 4 and 1. It doesn't matter what order you put them in, but it just means you have to put the columns of P in the correct order after that. So now this first column of P should be an eigenvector. For lambda is 4. And this one is an eigenvector for lambda is 1. Okay, so we can just put in what we found, or any scalar multiple, that's fine. And then you can check that this is true if you want. If you can always check your answer when you diagonalize, you can just multiply the matrices out, and you should get the same matrix A. Okay, so that's nice. We've diagonalized A, but I think the goal for this first part together is to kind of see what that means geometrically. So let's go back to T and see if we can figure out what that means. So I'm going to save this, and I'll erase this. So diagonalizing, as we know it, is just a kind of a nice way to keep track of all the eigenvalues and eigenvectors. Okay, but let's actually go back to T. So I've drawn here in the worksheet, I've drawn R2, but with different coordinate axes, right? We've drawn R2, so here's our normal R2. Let's see, I'll do our normal R2. You have an x-axis and a y-axis that you're used to. And these give you coordinates, but we've learned that there's no kind of natural coordinate system on R2. You can pick any coordinate system you want, and so we're going to pick a coordinate system that has these eigenvectors, right? Because we know A is diagonalizable, so we know there's a basis of these eigenvectors. So we're going to draw a different coordinate system that has these eigenvectors as the x and y axes. So the x-axis we'll do as 1, 1. I think I've done the other order on the worksheet. But we'll do 1, 1. So this will be our x-axis. And then -1, 2 will be our y-axis. Right, and now we have a different coordinate system. Right, we have this like 1, 1, -1, 2. I think you should probably look at the worksheet. There's a better drawing of these axes than I'm about to draw. But you have a different coordinate system now. Something over here. Okay, that's not drawn to scale. Okay, so for example, like this point, let's see, I think this point in our new system would be 2, 1. And that's what we have here. So let's see, we have V is 2, 1 in our new basis. So let's call this basis something. So let's put B. So B here is our eigenvectors. I guess the other way. 1, 1. Okay. So let's now I don't know what step we're on. Let's write a matrix for T in the basis B. Okay. So again, T is going to be, let's call this matrix something. Like T is going to be, or the matrix for T in this base is going to be 2 by 2. Right? And what we should do, this first column, we're writing it in the basis B. So we should look at T of B, 1. T of B1. This is B1. And then we should write that again in the basis B. Okay, and then likewise, this should be T of B2. But we're writing it in the basis B, so we should write this in the B coordinates. So it's similar to what we've done before. Right, and now we can just compute this. So T of B1, so we want T of 1, 1. Right, so T of 1, 1. Well, we already have a matrix for T in this standard basis, so we can just multiply A times 1, 1. Right, but I mean, we could multiply this out if we wanted, A times 1, 1, but we actually know something about 1, 1. It's an eigenvector. So this should just be 1, 1 scaled by your eigenvalue. Right? So you can actually work this out if we wanted to. Maybe I'll put it over here. Yeah. Right, so you get 1, 1. Right, and now we want to take this 1, 1, and we want to write it in the basis B. So we should get 1, 0. Okay, so this is going to be, since I reordered my basis on that worksheet, this is going to be the reordering of what we have up here. But yeah, I'll leave it like that for now. Okay, and we do the same thing here. T of B2 is A times B2, negative 1, 2. But I mean, this is eigenvector with eigenvalue 4. So we know what this is. Okay, and now we write this in our basis B. This should be 0, 4. Which is exactly the same as this diagonal matrix if I had chosen my basis in the correct order. Right, so this is what diagonalizing does for us. We're finding a basis. So diagonalizing is finding a basis finding a basis of Rn, in this case R2, so that T is a diagonal matrix when written in the basis. When written in the basis. Sorry, it's a little smushed. Let's do some other color. Yeah. And so the rest is just kind of summing up on the worksheet. I mean, why would we like this? Well, it makes things nice to compute. So if I had this basis already found, then I should really just convert all of my vectors to this basis, and then it's just pretty easy to figure out what T does to things, because it just, it's a diagonal matrix. It's very easy to multiply by a diagonal matrix. And so that's kind of why we like it. They give us, so we start with some vector space, T from V to V, and diagonalizing kind of gives you just a natural coordinate system on V, for which T is just a really nice matrix. So you don't need it, because some vector spaces don't come with like these standard basis vectors, and you kind of want to choose a good coordinate system. And the best one to choose is one where you get a nice matrix at the end. And we're going to learn, in the coming weeks more about diagonalization. For example, there's better bases than just a basis of eigenvectors. I think next week we'll talk about a basis of eigenvectors that are also perpendicular to each other. So we'll talk about that soon. Okay, so in the meantime, we can do some of the problems if there are no questions.
Yeah, I have a question about, it's one of the problems in the homework. So basically we said, A, like, that A is diagonalizable because it's an n by n matrix and it has n distinct eigenvalues, right? One of the problems in the homework was to prove why this is true.
Okay.
And I mean, I just thought of it as because it has n linearly independent columns, but I didn't know exactly how to reason it.
Yeah, that's essentially it. Right? Because the definition of diagonalizable is that it should have eigenvectors that are linearly independent, and linearly independent eigenvectors. And if you have distinct eigenvalues, all your eigenvectors for each one are going to be linearly independent. So there's another fact which you're using, which is eigenvectors for different eigenvalues are linearly independent. And so what you said is true, is kind of the reason why this is diagonalizable, is that if you have n distinct eigenvalues, you take an eigenvector for each one, you're going to get n eigenvectors that are linearly independent, and so that's a basis.
Okay, cool. Thank you.
And do people have other questions?
Yeah, I also have a question. So when you're writing the when you're putting the eigenvectors into a matrix, I guess conceptually, what does that mean? Because the eigenvectors are kind of in different eigenspaces, so how can you just put it into the same matrix? I don't know if that makes sense, but.
Well, we're kind of, I mean, this P matrix, when we're building this P matrix, what this really is a change of basis matrix. This is really, I mean, you can think about this as a change of basis matrix. And so if you're thinking about it like that, then even though your eigenvectors live in different eigenspaces, there's still a basis. Altogether, they form a basis. And so you're just kind of filling the columns of this with basis vectors. I think a good example will be number 1 on the problems, where we have a 3 by 3 matrix, and we want to diagonalize it. So I think we should do this, because then we'll see, I'll draw the 2 eigenspaces, and we'll see what they look like, and then I'll try to draw it here. And then we'll see what P is. So I think this is maybe a good example to start out with. And I give you that it has eigenvalues 2 and 8, and I want you to diagonalize it, or explain why it's not diagonalizable.
So because of the theorem, it's a 3 by 3, but there's only 2 distinct eigenvalues. So that means it's not diagonalizable.
Yeah, so careful there though. This is a classic trap that everyone makes, which is that this theorem says that A is diagonalizable if there are n distinct eigenvalues. So it's only one direction. So one thing to note is the warning. If this is not true, if you don't have n distinct eigenvalues, it doesn't mean you're not diagonalizable. So I'll say, yeah, if you don't have n distinct eigenvalues, this does not imply A is not diagonalizable. Because the true definition of diagonalizable, the real definition is that it's a condition on the eigenvectors. Right? That's why we use this. That's why we use this other theorem below here, theorem 1, theorem 2. That's why we needed theorem 2 to say why theorem 1 is true. Is because there's a condition on eigenvectors for different eigenvalues. Yeah. So the hint is you need to find all your eigenvectors. So hopefully people are working on number 1, and then we can go about putting P together. Okay. So one's a little annoying because you have to find a characteristic polynomial, which is a cubic. So maybe I'll also give you a hint: is don't expand factor. So I'll kind of work through this one because it's a 3 by 3 matrix. So it helps not to actually multiply everything out, but to pull out some like terms. Or in fact, if I just give you the eigenvalues, in fact, we just need to find eigenvectors. So in fact, never mind. We don't even need to find the other eigenvectors. I've already given you the eigenvalues. So to find eigenvectors, we want to solve for the null space. So if we row reduce, we get 1, 1, 1, 0, 0, 0, 0, 0, 0. Okay, and now we can find our eigenvectors. So we have one pivot column, two free variables. So x1 plus x2 plus x3 equals 0. x2 and x3 are free. So we get that we can solve for x1 in terms of x2 and x3. And so we get x2 times some vector plus x3 times some vector. -1, 1, 0. -1, 0, 1. And so we find that the eigenspace for lambda is 2 is the span of these two vectors. Okay, and now let's do lambda is 8. Okay, so I'll write this out on the board. Okay, so this one might take a little longer. We have to put it in row reduced echelon form. So maybe I'll divide everything by 2. That seems like a good way to start. -2, 1, 1, 1, -2, 1. And there's a bunch of things we could do. Actually, I don't really want to multiply the first one by a half because I don't like fractions. So instead, I'll not divide the last 2 rows by 2. Okay, now it's easier. Now it's easier to zero out these 2's. So get 2 plus 1 is 3. 2 plus 1 is 3. So we're just adding row 1 to row 2 and 3. Okay, and I can divide these by 3. Or even -3, why not? Okay, and I can use my second row here to zero out the third row and the first row. So let me keep my second row the same. And then if I add the second row to the third row, I get 0. Or if I subtract it, I mean, they're the same. And then now I can do this. This is 1 minus 1 is 0. 1 minus a -1 is 2. Okay. And so we find now, okay, now this is, I mean, this is essentially in row reduced echelon form. Maybe I'll do one more step. 1, 0, -1. Just divided the top row by -2. Okay, great. Now this is in row reduced echelon form. Okay, so we have two pivot variables, 1 free variable. So, okay, sorry, it kind of went like around in a circle. Let me maybe do this. We have x1 minus x3 equals 0, x2 minus x3 equals 0. We solve for our pivot variables in terms of our free variables. We get x1 is x3, x2 is x3, this is x3. All right, so this is just x3 times 1, 1, 1. So we get that the eigenspace for lambda is 8 is the span of 1, 1, 1. Okay, let's divide here. Okay, so here, this is why we see we need to solve for the eigenvectors, because even though we have two eigenvalues and it's a 3 by 3 matrix, this matrix is actually still diagonalizable because we have three eigenvectors here that are linearly independent. These two are linearly independent because they span this null space. We saw that they're the two vectors that are a basis for the null space, for this eigenspace. So they're linearly independent. And like we said, eigenvectors for different eigenvalues are always linearly independent. So these three form a basis. So in fact, A is diagonalizable. So let me erase some stuff. So we conclude A is diagonalizable because there is a basis of eigenvectors. There is a basis, namely these eigenvectors, of eigenvectors. There's other things you could say for why it's diagonalizable. Another way to say this is the geometric multiplicities of each eigenvectors, of the eigenvectors add up to n, i.e., so I'll write that down. The geometric multiplicities of the eigenvectors add up to 3. So the geometric multiplicity is exactly the number of eigenvectors that span the null space. It's the basis, it's a dimension of the null space. This is geometric multiplicity 2, and this is geometric multiplicity 1. So if the geometric multiplicities add up to 3 or to n, then that means that your eigenvectors form a basis. So that means you have n linearly independent eigenvectors. So kind of going back full circle to what P is, how we could just kind of put these, that's not gonna work. How we could put these eigenvectors into the same matrix P is because even though they're in different eigenspaces, they still together form a basis for R3. So I'm gonna try to draw something here. I'll write that again. Ah. Okay, so I already can't really draw on the chalkboard, but we'll see if I can draw on this whiteboard. Okay, so we have our three-dimensional space, and we can draw these eigenvectors. So -1, 1, oh boy. It's kind of like, well, it's not drawn to scale. Here's -1, 0, 1. Here's -1, 1, 0. And then our last one is 1, 1, 1. Right, so, I mean, not drawn to scale. So these three form a basis for R3, and so A is diagonalizable because these are now our new coordinate systems. So P is Yeah, wait. Two, 8. Okay, so I'll let everyone kind of mull over what we've done. Maybe you can work on the true false in the meantime. But are there any kind of pressing questions at the moment? So we'll take a short break there then. It is, the hour's up, so we can kind of, you can, I'll be here till 12, but you're welcome to work on whatever in the meantime. Yeah, of course.